Alright, hello everyone. Previously we saw how to solve separable differential equations, alright, but often it's not really possible to, even in a first order differential equation, often it's just not possible to separate your variables like, some function of y with dy being equal to some other function of x multiplied by dx. Sometimes it's just not possible to separate the independent and dependent variables along with their differentials this way. Alright, so but sometimes we see that it would be possible to separate them. Like at the end we would get a separable differential equation if we make a certain substitution. But anyways, let me not get too ahead. So the thing is, I'd start by saying how, what we should basically look for. So suppose say we have a differential equation and we are able to put it in this form. Okay, so derivative y with respect to x, it's some function of y by x, okay. Now let me just clear up what this means. It basically means that it's a function, but the terms in it you can express all of them, okay, as y by x. Okay, suppose say like sine of x by y plus let's see, y squared by x squared. This would be a valid function of y by x. Why? Because okay, so if we just try to express it in terms of y by x, okay, so this is sine of 1 over y by x, okay, plus this one we see it's pretty obviously y by x whole squared. So as you can see, this is a function, okay, this is a function of y by x, right? Sine of 1 by y by x, and then we have y by x squared. So another way you could just think about it is, suppose you say that v, that some variable v is equal to y by x. Okay, so if that's the case, we can just express our function in terms of v, right? So this y by x, wherever we see that, we're going to replace that with a v. So sine of 1 by v plus y by x, again that's v, and you have a squared there. So as you can see, your function right here, at least the example that we were working with, it's clearly a function of y by x, and since we made the substitution, it's even easier to see that it's a function of v. Okay, or in other words, since v is y by x, it's a function of y by x. But anyways, that was just an example just to show you what dy by dx being equal to some function of y by x really means. Now what can we do with this? Suppose say we have some differential equation that we can bring to this form. So dy by dx is gonna equal some function of y by x, okay, and we'd need to have already tried separating the x and y variables. That's what we always should first try when we see a first order differential equation. So if we have already tried that and that doesn't work, and we see that we can actually bring this to this form, bring the differential equation to this form, there's actually something that we can do to simplify this. Okay, and for that, the thing is, this is in fact the substitution that we're gonna need. So suppose say we our differential equation in this form, okay, and I make the substitution. Okay, I let me move to the right now. I make the substitution. Well, I'll actually write this again here. So y prime is gonna be equal to some function of y by x. Okay, so and I make the substitution v equals y by x. Now this has quite a few implications here. Well, one thing is, if I want to express, actually my goal here, it's actually to eliminate y from everywhere in this differential equation. So for that, what I'm gonna do is express y in terms of v and x. Okay, for now I'll express y in terms of v and x. So this is gonna be y is gonna be x into v. Okay, x into v. So what does this imply? Well, one thing, as you can see, we are halfway there. Just by making the substitution, v equals y by x here, we should be able to get rid of y on the right side. Okay, on the left side we have the derivative of y. It has the y in there. What can we do about that? Well, we have this. Let's actually just try differentiating both sides. We should get something for y prime or derivative y. So what we get if we do that is, derivative y with respect to x. Okay, I'm differentiating both sides of this. Okay, so derivative y with respect to x, same as y prime. It's gonna be, okay, so product rule. First thing you need to differentiate this, keep that the same. So derivative of x with respect to x is just 1. So 1 multiplied by v, or just v, plus keep x the same, differentiate v with respect to x. Okay, so x multiplied by the derivative of v with respect to x. So yeah, the main thing is we can express dy by dx, like this. And now, what happens here? What happens here if we plug in this expression into our original differential equation? Okay, we're actually meeting our goal, because this is dy by dx, and if you just plug this in, we're gonna get on the left side, okay, from this differential equation, okay, using this substitution right here, this thing right here, okay, and also the fact that y by x is basically v, okay. So what we're gonna have on the left is, just this the expression for dy by dx. So v plus x multiplied by dv by dx. On the right side, what you're gonna have is f of y by x, but y by x, we just said that that's equal to v. That's just we named that a variable called v. Okay, now there's something really interesting going on here. Okay, and it's the fact that this is actually a separable differential equation. Might not be that apparent yet, but let's just try to separate the variables. Okay, so first let's bring v on the right side. So what we have is x dv by dx is gonna be f of v minus v. Now this should be pretty apparent. Let's multiply by dx on both sides and divide by x. If we do that, also if we divide both sides by this thing, okay, just to bring this to the left with the v, with the dv, so what we're gonna get is something like this. Is just a formality to prove that this indeed is a separable equation now. Okay, so what we have on the left side, if we bring this to the left, so 1 over f of v, some function of v minus v, dv is gonna be equal to, okay, so divide both sides by x, so 1 over x, and we also get the dx right here. So you have dx. Voila! This couldn't be any more clear that the fact that this is a separable equation in v and x. Okay, in v and x, because all the v terms are here. There's no x term here. It's all v here, and also it's all it's just 1 by x. But anyways, it's just all x here. Okay, so this is definitely a separable differential equation. We know how to solve that. We can integrate both sides and then find a solution. Obviously here we cannot express it in some way, because we don't really know what the function f really is. But anyways, the point is that this has become a separable differential equation. It really increases our odds of solving the equation. Alright, so if we solve that separable equation, we are gonna get some relation between v and x. Okay, some relation between v and x. Okay, so yeah, I'll just write it like this. Okay, so what does that give us? Our original purpose isn't to solve for v, it's to solve for the dependent variable or function y. So how do we do that? Well, we just reverse our substitution. We have v in this expression. Okay, so let's just back substitute. So v, as we originally said, is just y by x. If we do that, then we basically have an expression where you have x, okay, and also where you have instead of v, you'll have all the y by x's. Well, so obviously you have an x here with the y. Basically, what I'm trying to get at is you will have a relationship between y and x, which is basically our goal. Okay, the whole purpose of solving this differential equation is basically to get a function or relation between y and x, which we should be getting at the end, provided that we can take this integral, provided this is something that we can do. All right, so this is basically why this method works. If you see that you can put your differential equation in this form, your derivative of the dependent variable with respect to your independent variable is equal to some function of your dependent by independent variable. You can then make the substitution, v equals y by x, okay, dependent by independent variable, okay, and then using that, and we can use the product rule here, I think most people just memorize this portion, but it's really not necessary. You can just work it out every time. And basically what we see, all these things, to be honest, these are not something to memorize. It's just to show you the fact that we indeed do get a separable equation, okay, given all, we meet all the initial, we meet the initial criteria and make the substitution. And then at the end, if you can solve for, the integral on both sides, we should be able to get a relation between y and x at the end. So that's the goal here. Okay, so with that explained, the last thing that I want to talk about is, okay, so, how do we detect in any case, in any general case, when is, dy by dx of function of y by x, okay? And to be honest, usually it's pretty obvious, okay? Usually, if you have, just dy by dx, okay, and every other term other than this, every term other than this is some function of, y by x, or you can make it some function of y by x, okay? I'll just give a brief example here. Suppose, say, y squared plus 4x squared equals x multiplied by y. Okay, so I'm not testing for whether this is separable as it is, but the main point that I want to prove is that this should actually be pretty apparent to you, that it's gonna be, this is gonna match this form. Okay, this is gonna match this form, and even without actually solving for dy by dx, it's, to be honest, just comes with practice. The thing we can see here is, okay, let's just, it's kind of like the total power of n, x and y in all these things, other than dy by dx, they're the same. They're kind of like 2 each. Okay, so if you kind of like divide by x squared here, let's see what happens then. Okay, so y squared by x squared, what you get here, but basically we can write that as y by x squared. Okay, then you have, dy by dx. I'll just write that as y prime. 4 x squared by y squared, x squared by y squared, x by y whole squared. Well, x by y, you can actually just write it like this. And again, this is a term made up of y by x. And then you have x by y. If you divide that by x, you get, so not x squared, you get y by x. And now it's pretty apparent that even without having expressed dy by dx explicitly, like just having this on one side, it's pretty apparent that all the terms are in fact dependent on or functions of y by x. So this is our first order homogeneous differential equation. Okay, but however, if sometimes this isn't apparent, we definitely need some foolproof method. And that foolproof method is, suppose, say, we are suspecting that there's some, suppose, say, if we are suspecting that dy by dx is some function of y by x. Okay, first thing what we need to do is actually express dy by dx equals the other things on the on the other side, on the right side. So first thing we need to have to bring the differential equation to this form. Then what do we do? How do we recognize whether it's homogeneous or not? Well, there's a pretty neat trick in this function. Okay, in this function, let's try substituting. Instead of y, let's put t multiplied by y. Okay, instead of y, let's put t multiplied by y, and instead of x, let's put t multiplied by x. Okay, if we do that, what do we get? Okay, if we do that, here what we'll get is, this is gonna be f of ty divided by tx. Okay, and this is basically f of y by x. All right, now this is pretty interesting. Is we made these two simple modifications, substitutions here, but our right side didn't change, and this is basically how in general, in any general case, okay, no matter how convoluted it might be, you can test. Okay, this is basically your test. Okay, Okay, I'll write it in big caps right here. So this is basically a test for whether you have a first order homogeneous equation in your hands or not. So you make these two substitutions, place ty instead of y, place tx instead of x. And t is just some constant, and the thing is, you should, after the substitution, you probably have to do some cancellation with the t's and all. But if it is a first order homogeneous differential equation, the t's will cancel, and your differential equation, okay, your differential equation is gonna be the same as it was before, okay, same as it was before. So DE, the differential equation, will be unchanged, all right. So you can more formally say that, suppose, say, first thing, you have a first order differential equation, first order DE, okay, and then you obviously, since it's a first order, okay, you can obviously express it as dy by dx being equal to some function, let's say g, it's a g of x and y, okay. This you can do in any case if you have a first order differential equation. Now, if this is gonna be a homogeneous equation, or basically your right side is gonna be a function of y by x, what you can do is, same thing here. I'm just restating that in kind of like a more formal way, okay. So if you put in tx instead of x here and ty instead of y here, okay, so you're gonna have g of tx and ty, and as we said, this needs to be, if this side indeed is a function, is indeed actually a function of y by x, okay, function of y by x, your t's would cancel, and the right side and the whole thing actually would remain the same as it was before. So this should actually reduce to, okay, or actually be the same as before. It should reduce to just g, the same function g of x and y, okay. So that's basically your test for finding whether you have a first order homogeneous equation in your hands or not. Okay, so that should be the end of this video. Today I just wanted to discuss the strategy and basically why this method works, okay, and what's the basis for this. I'll do quite a few practice problems in the next video, hopefully. So see you then. If you like this video, please do leave a like, please subscribe, and study smart.